Welcome back for our final installment of Lecture 5, Lecture 5E. So today we're going to be looking at Walsh diagrams. So what is a Walsh diagram? Well, we use Walsh diagrams in order to determine possible geometries using point groups and molecular orbital diagrams, or even more important, not so much possible geometries, but the most probable geometry. So sometimes you also hear this called correlation diagram, a Walsh correlation diagram. They do have an arrangement of names, so you may hear any of those terms. But the premise of a Walsh diagram is that a molecule will adopt a structure that provides the most stability, which again means the lowest energy, for its highest occupied molecular orbital, its HOMO. So that's the highest level that has electrons in it, and we want to make that as low as possible. So what we're going to do is you're always going to compare two different structures. And so we're going to start with the most symmetric possible version of the molecule, and then we'll distort it to a version that has a lower symmetry. So let's look at water. It's one of the more simple molecules, and it's a good place to start to explore Walsh diagrams. Now, we know that VSEPR predicts a bent geometry, but let's see what molecular orbital has to say. Molecular orbital theory has to say. So here we've got our two possibilities for water. If water were linear, it would look like this, and it would have a geometry of D infinity H, just like the BEH2. So this will allow us to use the molecular orbital diagram we did for BEH2. And then over here we have C2V for water in that bent structure that VSEPR says it is. So we don't always necessarily trust what VSEPR has to say for geometry. It does get some geometries wrong. Ordinarily, it's very good, but its reasoning is not particularly sound. And so we do have a better grasp of molecular orbital theory and why things are doing what they're doing, particularly looking at symmetry and energies of the orbitals that combine to give a particular geometry. So we want to compare D infinity H and C2V in terms of molecular orbitals and their geometries. So we do have to look at some rules for how we are going to adjust our energies. So rule 1 says that if lowering the symmetry creates two orbitals of similar energy and the same symmetry, these orbitals will mix and split in energy. We'll see an example of that with this transformation. Rule 2 says if we increase the amount of bonding between the central atom and the pendant atom, so AX bonding, it's going to decrease the orbital energy. It makes sense, more bonding, lower energy. If you increase the amount of anti-bonding between those orbitals, then the orbital energy is going to increase. And rule 3 says if we increase any presence of pendant-to-pendant bonding, so XX bonding, it will make the orbital energy decrease. Again, we always had in the past said these two things don't interact, but if they get closer, there is always a little bit of interaction, and so there may be a small change in the energy. So if you increase the bonding character, the energy will decrease slightly. If you increase the anti-bonding character, then the orbital energy will increase slightly. Now, what happens if you're dealing with two different rules and maybe something that makes it increase and something that makes it decrease? How do we know which one will take precedence? Oh, and I forgot to mention here, this increase can be caused by a distortion of a molecule. Okay, so getting back to the question, how do we know which rule takes precedence? Well, rule 1 has the largest energy impact. And so if you have something, an interaction that's following rule 1, then that will dictate whether energy is raised or lowered. If you had a combination of like 2 and 3, rule 2 has a greater energy impact, so that would take precedence. And if you only have rule 3, then you just have rule 3. But rule 1 is greater than rule 2 is greater than rule 3. You always follow the rule that has the greater impact. All right, so let's take a look at what we did for our linear BEH2. We had an orbital diagram that looked like this. When we're doing our Walsh diagrams, we are only going to concern ourselves with the central molecular orbital diagram. We are not going to worry about the atomic orbitals on the side, but this is the part we want to look at. So we'll have that to start with. So we always start with the more symmetric version and then move to something that is less symmetric. And again, you can compare your symmetries by comparing the H values. Remember that for that linear version when we did BEH2, H was equal to infinity, and for our bent version, H was equal to 4. And so since infinity is greater than 4, we're going to start with the higher H value, our linear geometry, and then we're going to distort it to a bent geometry and compare the energies. Okay, so for our sigma G plus, we've got a linear arrangement here. Whoops, don't want to draw. We've got our linear arrangement here. We have our bent arrangement here. And so we really haven't changed the interaction between the S's of the pendant atom and the central atom. So that doesn't change the energy. However, notice that my pendant atoms are now closer and they are in phase. And so that's a bonding interaction. And so because my distortion caused this tiny bonding interaction here, it does lower the energy just a little bit. But these energy changes due to bending are small, but they do go down. And so this follows rule 3 that says if you increase the bonding interaction between your pendant atoms, then the energy will decrease. Let's look at the next level, our sigma U plus. And so here we go down again because we're going to a bent geometry. And here, remember for a p orbital, most of your electron density is centrally focused in that lobe. As you go to the outer parts of the lobes, the electron density isn't quite as high. So when we bring these to a bent geometry here, notice that we don't interact as much with the areas of the orbital that have a higher electron density. So we're lowering the bonding interaction there. And so rule 2 here makes the energy go up. Now notice also that my pendant atoms, my hydrogens here, have opposite signs. And so if they interact, they would have an anti-bonding interaction. When I move those down into a bent arrangement, I'm bringing 2 orbitals closer in an anti-bonding arrangement. It's a small effect, but it's an effect nonetheless. And this also makes energy go up. And so the net change going from a 1 sigma U plus in the linear arrangement to the 1B2 in the C2V arrangement, that causes energy to rise a little bit. Now here we have something that they both had these non-bonding orbitals here, the px and py, and so they are a wash. They just go directly across. Here they're just called the pi u. Here they're the 1b1 and the 2a1. They do have different symmetries here. My sigma G plus here, very similar to the sigma G plus down below. It's the sigma G plus star here. So here I'm in a linear arrangement. It's anti-bonding between the oxygen and the hydrogen because they have a different phase. So we go to a bent arrangement and these got to swing around down here. Now notice what's happened. This is different from what we saw in the sigma U plus. I'm moving my 2 pendant atoms here closer together, and so I am also increasing a bonding interaction between this hydrogen and this hydrogen. It's a small effect, but it's an effect nonetheless. So this follows rule 3, and notice that my energy drops just a tiny little bit. Okay, now the next orbital we have is this very top one. Very small interactions. We have 2 competing interactions here as we go to this bent arrangement here. So just like before, by moving this orbital down, I'm lessening that interaction. So I'm actually lessening the anti-bonding interaction here and here, I am creating an anti-bonding interaction here. So rule 2 here, because I'm decreasing my anti-bonding interaction, the energy is going down. But according to rule 3, I'm increasing the anti-bonding between my pendant atoms, the energy is going up. So which one takes precedence? Well, rule 2 is always a bigger impact than rule 3, and so we're going to say that the energy drops just a little bit. And so that's what we have here, is the energy dropping from linear to bent. Now, we're going to complicate this a little bit. And the reason we're going to complicate this is because of the 3A1 and the 2A1. Remember, this 3 and the 2 are just because this is the second A1 in this molecular orbital diagram, and this is the third A1. They both have A1 symmetry, and they are fairly similar in energy. They are close in energy. And if you have two orbitals that are close in energy and have the same symmetry, they can interact. And that's what we're going to have happen here. We're going to get orbital mixing. So we're going to mix that 2A1 and the 3A1 sulk. So this is just a p orbital with one of the sulks interacting with the oxygen atom. So what's going to happen? Well, same as before, when we were looking at S&P mixing for our heterodiatomic molecules. We can interact in a positive reinforcement way or a negative destructive way. So here we're going to have our non-bonding p orbital plus the anti-bonding molecular orbital that we have here. And then we're going to interact by changing the sign of this for the destructive. And so when these two things get together, I'm going to get this. So this lobe is going to interact with that, and it's going to create a much bigger portion down here. This and this is also going to interact. It's going to cancel out some of that part of the lobe, and so it's going to be kind of tiny up there. The result is a molecular orbital here that is strongly anti-bonding. If I look at the other side, I have something like this, and when I add those together, I get something that looks like that. So this lobe and this one here will create a large phase up here. The white down here and the brown here will cancel out and create a small one down here. And this turns out to be just slightly bonding. So strongly anti-bonding is going to increase the energy of this combination, and the slightly bonding is going to lower it just a little bit. So let's look at the impact that has on our Walsh diagram. The orbitals down here were unaffected. They're not impacted by that mixing. The 1B1 is the 1p orbital that was not affected either, because we used the A1. But we said that the A1 here, the 2A1, one of those went down in energy, and that was the one that created a slightly bonding. And then the other one became strongly anti-bonding, and so that went up in energy here. And of course, this is the 2B2 up here still remains the same. It wasn't impacted. But this was what it meant by if you have two orbitals that have the same symmetry and are close in energy, they can split and will form two additional orbitals. And so we have these here. Now what we want to do is to see which of these is going to be the more favored geometry. Well, let's put in our electrons. So we know that H2O has 8 valence electrons, 6 from the oxygen and 2 from the hydrogens. So let's fill in 8. So we got 1, 2, 3, 4, 5, 6, 7, 8. Okay, and if we do this guy here, we have 1, 2, 3, 4, 5, 6, 7, 8. Now, if we compare the highest occupied molecular orbitals, they're actually exactly the same, because this orbital has the exact same energy as this orbital. So we go to the next lower one. The next lower one is this one here that has the same energy as before because it's degenerate. But for the bent structure, the next one comes down here. And so this mixing of the 3A1 and the 2A1 actually is what creates this structure to be more favored than linear. So that finishes out lecture 5. A lot of complex material in here. So if you don't understand any of it, make sure that you come to the Panda sessions, ask lots of questions, contact me, email me, come see me in my office if you need some help going through any of these. Otherwise, best of luck.